Hello everyone, my name is Jie. It's my pleasure to give a presentation at the domain-specific modeling workshop. I am a graduate student from Beijing Institute of Technology and currently doing some research on model-based system engineering. Today, my topic is integration of modeling and verification for a system model based on common language. The content of this presentation is divided into 5 parts. In section 1, I will give an introduction of the background of my research. And in section 2, the related works about modeling and verification will be introduced. I will introduce how to integrate modeling and verification of system behaviors in our methods in section 3. And the case study based on the proposed methods will be illustrated on section 4. Finally, I will give the conclusion and future works at section 5. Firstly, let's focus on the introduction. With the rapid growth of system complexity, model-based system engineering has been increasingly used in the development process of the complex systems. MBSE makes use of formal models to support system requirements, design, analysis, verification, and validation activities. However, the development process of complex systems is a multi-domain process. Different model languages, such as UML, SysML, BPMN, SQL, etc., and different modeling tools, MagicDraw, computer modeling, etc., are developed to support the multi-domain process. When using MBSE to model complex systems, models are created from different perspectives within different modeling languages. For example, BPMN is used to describe the system from the perspective of business process, and the SysML focuses on the function and composition of the system itself. The existing tools may support several languages. However, supporting most modern languages on the same platform is a difficult task. We need a way to describe these models building in different model languages uniformly. The MBSE abstract system model are developed in the requirement and architecture phase of the V model, and it will use the system model as a single source of truth to guide the subsequent development process. This is why we need to verify the correctness of the system model in the early design phase. The early design system model enables to represent the solution of the development system across the entire development process. But how to verify? In this paper, we choose the system behavior models. System behavior models can describe the dynamic characteristics of the system. The verification of behavior models can prove whether the functional and the performance requirements of the system are met, thus reducing the errors. As we mentioned before, different modeling languages and tools are used to develop models in different domains. At the same time, different methods and tools are used to verify heterogeneous behavior models. It is necessary but difficult to adopt a unified integration platform to support the modeling and verification of heterogeneous system behavior models. So, we want to propose an approach to uniformly describe and verify different domain system behavior models, and then to develop an integrated tool for system model modeling and verification. Next, I will talk about the related works about modeling and verification. From literature review, we summarize the 3 methods to verify behavior models, including formal verification, simulation, and executable models. In the formal verification methods, behavior models are verified by transforming the model into the input language of an existing formal verification tool. Verification based on simulation is usually implemented by transforming the system model to a simulation model. Verification based on executable models is realized by extending the syntax of the existing model languages, such as UML. These 3 kinds of methods can realize the verification of system behavior built by 1 or 2 modeling languages, but they lack the ability to integrate modeling and verification of multi-domain behavior models in a uniform way. And we will provide a solution for it in section 3. I will introduce the main part of my presentation. Integrate modeling and verification of system behaviors. First, the unified formalism of multi-domain system behavior models based on common language will be introduced. And then we will integrate hybrid automata to comma to support system behavior verification. The unified formalism of multi-domain system behavior models is based on the GeoPPRE modeling approach. And the foundation of the GeoPPIE approach is the MOF framework, as shown in the left figure. There are 4 layers in the MOF, M3 to M0. Lower layer elements are instances of upper layer elements. M3 refers to meta-meta models, which are the basic elements of the constructed model compositions. M2 is used to define models in M1 layer. Modeling languages such as Smile is defined based on meta models. M1 represents the model layer. Models can describe real systems in an abstract way and enables to support system development. M0 refers to the perspective of real systems, which is abstractly described by models in M1 layer. In the MOF framework, meta-meta models in M3 layers are the foundation of the entire modeling framework. The GeoPPRE meta modeling approach has 6 meta models. Graph refers to a collection of objects and their relationships. Object refers to the basic entity in the graph. Relationship refers to the association between objects, connected to objects through rows, and one relationship instance contains 2 row instances. Property refers to the attribute of the 5 other meta models, and point describes the one point in objects. Row is used to define the connection rules pertaining into the relevant relationship. Extension refers to the additional constraint rules used to construct meta models. Connector is a kind of constraint rule. And in the GeoPPRE meta modeling approach, an instance of a GeoPPR meta model is a GeoPPR meta model, such as the graph meta model. And an instance of the GeoPPR meta model is called a GeoPPR instance. The semantic modeling language Comma is developed based on the GeoPPRE meta modeling approach, as shown in the left figure. The syntax structure of Comma is designed according to the GeoPPRE approach. It uses meta model classes to describe GeoPPRE meta models, and it uses model classes to describe GeoPPRE instances. A simple Comma model is described by a model class, as shown in the right figure. Then we use Comma to express the 6-mile state machine diagram and the BPMN. As shown in the left figure, different GeoPPR meta models are developed by Comma to support different concepts in STM and BPMN. For example, we can use the object meta models to express concepts such as start state, final state in STM, and process, task, start, and end events in STM. These meta models are developed based on Comma by adding semantic concepts of STM and BPMN. For example, the object meta model is instantiated as a state object meta model by adding object state semantics. So Comma can support unified expression of multi-domain behavior models. It lacks syntax to express the behavior precise enough to support for the dynamic verification. So we integrate the hybrid meta into Comma. Hybrid meta can be processed as a tuple. Log is a finite set of discrete states. H is a set of transitions between these states. X is a finite set of variables, and initial is a set of initial states. Invariant is a set of invariants which can set a value constraint for each state. Flow can be expressed as equations, and jump is a set of functions which consists of a guardian or assignment. Event is a set of discrete events. In order to integrate the hybrid automata syntax into Comma, we established the mappings between HA directed graph and Comma. The directed graph can express the HA model, and the Comma model has similar expressibilities to the directed graph, so we can also use the Comma model to formally express the hybrid automata model. For example, we can use the Comma model to express the hybrid automata, and we can use the object instant to express the log and the initial state. And we can use the property instance to express X, events, invariant, flow, and jump. Then the syntax of hybrid automata is added into Comma language. 3 declarations, variable declare, event declare, equation declare, are used to describe variables, events, and flows in hybrid automata. And the state object instance is used to define one state. And the group object instance is used to declare object instance whose variables and functions can be used by other object instance. Initial declare is used to identify initial state. Transition declare is used to declare transitions of relationship instances which contain scarce effects and the new state. Function declare is used to declare user-defined functions. The right figure is a simple example with behavior syntax. The object idle is the initial state identified by the keyword initial, and the equation will be executed in this state. The transition clause is defined in the relationship instance transition 1, and it means that if the event start occurs, the system will transform from idle to moving. The verification of behavior models is realized in MetaGraph as shown in the following figure. The Karma behavior model is built in MetaGraph. Users can add the behavior syntax to the model using the related configuration window, and the syntax added will be synchronized to the Castro Karma model. And then the simulation compiler will transform the Karma model into a sim file, and the sim file will be inputted into a hybrid Automata solver, which is a simulation solver based on C specification to simulating the hybrid Automata. And finally, we can get the verification results. Now we will use one case to evaluate the proposed approach. In this case, an unmanned vehicle needs to go to a place 350 meters away for a detection task, and the unmanned vehicle will adjust its speed according to different conditions. The acceleration of the unmanned vehicle in different conditions is shown in the table, and the unmanned vehicle should reach the detection destination within 30 seconds. Based on the scenario we talked about, a 6-mile state machine model for unmanned vehicle driving is created using Karma as shown in the right figure. Now we can add a behavior syntax to the Karma model through the configuration window. The algebraic variable acceleration is used to describe the acceleration of the unmanned vehicle in different conditions. And another algebraic variable modification is used to judge whether the road is smarty or not by the user-defined function is smarty. And the function is declared in the controller. The controller is a group object instance. And two continuous variables, velocity and distance, are used to describe the speed and the driving distance respectively. Also, we can add equations of functions for object instance and add transitions for relationship instance. In this PPT, a part of STM Karma model with behavior syntax is shown in the right figure. As we can see, for transitions A, B, C, D is taken as examples. The transition A means if the event instruction happens, the system will go to the start moving state from the idle state. And the transition B means that if the time is greater than 3 seconds, the system will go to the normal moving state. And the transition C means that when the modification is forced and the velocity is less than 16, the system will go to the accelerate state from the normal moving state. And the transition D means that if the modification is true and the velocity is greater than 8, the system will go to the decelerate state from the normal moving state. Then the STM Karma model is compiled by the simulation compiler to generate a sim file. The generated sim file is executed by hybrid Automata solver, and the simulation results is shown in the following figure. We find it takes 29.01 seconds to reach the destination, which means the unmanned vehicle reaches the destination within 30 seconds. So the STM model is correctly constructed. Finally, I will give the conclusion. First, we proposed a unified modeling and verification approach for multi-domain system behavior models based on Karma. And the theory of hybrid automata is used to realize the verification of Karma models. Through case study of the verification of a STM model, the effectiveness of the proposed approach is validated. In the future, the reviews of one Karma model's property is considered, and optimization of the Karma language syntax and semantics is considered. That's all. Thank you for your listening.